Okay, now I continue with a minimum mean square filter. So that is the MMSE, that is minimum mean square error. And sometimes it's also they call it the winner. Yeah. Application. Or channel equalization. Channel equalization, channel estimation, and signal detection. That's the application. And how we develop this? How the important that how we calculate the filter coefficient. The structure of the filter is similar to the zero forcing filter. So in this case, we use also the finite input response filter. Yeah. So the structure of the filter, that's the digital filter. So they consist of the number of filter tabs, and with each filter tab they have a capillary. Yeah. Here is one capillary. Here one capillary, and here is the filter coefficient. Yeah. And as I said in the today morning session, the filter coefficient can be computed one time before simulation, or it can be adaptively calculated according to the channel coefficient. It means that it can be adaptively updated according to the channel state information. So if the filter is adaptively adapted, then we have a so-called additive filter. We have so-called additive filter. Adaptive. Actually, the additive filter application, the additive filter is very wide, not only in the wireless communication. And now we introduce you how to calculate the minimum square error filter. It is actually how to calculate the filter coefficient. Yeah. And as I said before, in order to calculate the filter coefficient, yeah, we need to develop a cost function. And the cost function is defined as a expectation of the different value between the receiver signal to the transmitter signal, yeah, and square value here. And we can do the estimation here, expectation here, and the purpose of the filter is to minimize this error, And here's the cost function. And in order to minimize this error, so you need to follow my calculation. Here, please set up n. That is the output of the filter. That's the output of filter. That is the conclusion of the channel coefficient with the input filter. Yeah, with the input and filter. So we have this is that is the input. That's En, and Cn is the filter coefficient, and Zn that is the output. And the output is the convolution of the input with the filter coefficient here. The result is the output. So that is the Z equation here. That is this equation here. Yeah. Convolution of the filter coefficient with the input And here is a conclusion operation. M is the index from minus n to the plus n. Yeah, that is famous in the some other lecture like signal processing or digital signal processing, etc. Yeah. And now we just replace this form to the code function. Yeah, you replace the set n in statistic one. Yeah, to this code function. Yeah. And now we have a new code function in terms of this this term, and this term subtract to this term. Yeah, that's a new code function. And now we need to find the filter coefficient, Cn. Cn is a variable, need to be optimized or need to be found. So in order to minimize this code function, yeah, minimize this code function. And in order to minimize this code function, you need to derive the code function in terms of the filter coefficient. Yeah, you need to derive the code function in terms of filter coefficient. Yeah. You have two n plus 1 filter coefficient. So now you observe for one filter m index. Now we derive it, yeah, to the filter coefficient here, and you have this result. Yeah, you have this result. Yeah. You have this result. You derive this the coefficient in terms of the filter coefficient variable. So you have this results. Yeah, you can check it at home actually, or you can check it from my slide, and it result in this term. Yeah, this term. Yeah. So this term is expectation of the different input and output. Yeah, with the difference between the output and filter with the transmitter signal, with the multiplication with the input of the filter. So here is set n minus x n multiplied with y n minus m. Yeah. And now it's a very important information. Yeah. You need to minimize the code function here. You need to minimize the code function here. The code function here. You need to minimize this code function, and you need to let the derivation output become zero, in order to minimize this code function. Yeah. Now you are setting the filter variable somehow that the derivation result should be 0 in order to minimize the code function here, and it result in this equation, this relation, this equation. It means that you let this term become 0. You let this term become 0. Yeah. So we have this term multiplied with this term is 1. Yeah. Should be equal to this term multiplied with this term. Yeah. Okay. So that is very important. Yeah. So this term should be equal to this term to let this function become minimized or to minimize this function. And now you have an equation. You have equation. You need to solve the filter coefficient in order to have a equal this function. Yeah. And now you have you can replace set n here from this equation to this equation, and you have this the next equation. Please so just have a look on the slide. So this term replace the set n by using this relation to the condition of the derived equation here. So we have this relation. Yeah, this relation. The next step, the next output. In this output, yeah, you have some relation. That is a summation and the filter coefficient. So you can put outside from the expectation function. So this term you can put outside, and the expectation you can put inside here. Yeah. Then you have a next relation here. So that's the expectation of the input, the signal input of the filter. And here is the expectation of the transmit signal with the receiver signal. Yeah. So Y is the receiver signal. Yeah. Y is the receiver signal. Yeah. And H is the transmitter signal. Okay. So you have those slides, so you can have a look. And now you need to check this relation or this definition. Very important. Now you have the correlation or the expectation of the input signal and here transmitted signal. So that's the cross correlation function. Define cross correlation function. And this Y N, that's the cross correlation function of the transmitted signal with the receiver signal. Yeah. So R is Y N. That is cross correlation function. Yeah. Of the transmitted signal with the receiver signal. And next we can define the autocorrelation function. Yeah. That is the expectation of the receiver signal here with also it itself. Yeah. And then we obtain the following relation. Yeah. With a new definition. So we can come from this relation to this relation. And you know that here you can see that is the multiplication of the channel coefficient with the correlation coefficient, just autocorrelation coefficient, and here's the cross correlation coefficient. And here we observe for a different k. Observe k from minus n to the plus n is k equal to minus n here. So we have one relation. That relation here. So from this equation, you just replace k is equal to minus n. Yeah. Minus n. Yeah. Then from k from minus n to the plus n. Yeah. And also do it in the also for other k here, k equal to 0, k equal to n. Yeah. As the final, we have this relation. Yeah. So in this relation, you can see, we have a autocorrelation matrix. The autocorrelation matrix multiply with the filter coefficient, result in the cross correlation matrix. We have the autocorrelation matrix. That's autocorrelation matrix of the receiver signal. Yeah. Multiply with the channel filter coefficient vector. Yeah. Yeah. Result in the cross correlation vector of the transmitter signal with the receiver signal. Yeah. So in the more shorter vegetation, yeah, more shorter. Yeah. So we have we can rewrite it in the matrix form. Yeah, matrix form. Yeah. So we have here is the cross correlation matrix. Cross correlation matrix of the receiver signal here. Cross correlation matrix of the receiver signal here. And here is the here's the auto correlation matrix of the receiver signal. Here's a vector of the filter, and here's a vector of the cross correlation of the X, that is transmitted signal. Y is the receiver signal here. And now we have a relation between the channel coefficient here. And here is the cross correlation, autocorrelation matrix, and here's cross correlation vector. So that Y is the receiver signal and X is transmitted signal. And that's not difficult to come to the next equation. In this equation, show you how to obtain the filter coefficient by using the minimum mean square of filter. Yeah. And this the filter coefficient by using the middle mean square error filter. That is the multiplication of the autocorrection matrix, inverser of the autocorrection matrix with the cross correlation vector. Don't be remind that that here is a y receive theta and here x is transmitted theta. So in order to have a optimal filter, in order to compute the optimal filter, we need to know the autocorrection matrix of the receiver signal and also the cross correlation matrix of the receiver signal with the transmitted signal. Yeah, that is the condition in order to implement the mean square error. Yeah. Okay, so I have introduced you a theory of the mean square error filter. You see that there are also a lot of mathematical calculation. Actually, it's not easy to understand. Yeah. Sometimes it's very hard to understand the mathematical description. But if you are working on this field, you can have a very short derivation, then you can understand full. Yeah. So that is application in the channel equalization. I have also show you some application in the channel estimation. In the channel estimation. Yeah. In the channel estimation. In the channel estimation. So we can use the mean square error filter, to estimate the channel. Yeah. Especially for the time invariant channel, for the wireless channel. We can also estimate using the mean square error filter to estimate the wireless channel. And here is an example, to deploy the mean square error for the for the I draw is for the OFM system. Yeah, OFM system. You have in OFM system you describe the signal in the two-dimensional domain. One is the time domain. I'm sorry, here is the frequency domain, and here is the time domain. Yeah, it's the time domain. And here is the amplitude or the power of the signal. Yeah, here is the signal. And actually, in the OFM system, here is the dimension of the subcarrier, and here is the dimension of the OFM signal. Yeah. In the dimension of subcarrier, or in the dimension of the time domain, I'm sorry, the frequency domain here, or the subcarrier here. So there is an effect which affected on the opacity of the system. So affected the orthogonality of the system. It influences the orthogonality of the system. That is a Doppler spectrum. The Doppler spectrum. And I have introduced in my last 2 days lecture the Doppler spectrum. Yeah. Match you have introduced the frequency, the carrier frequency offset. Yeah. So it changes the carrier frequency at the receiver. So the Doppler frequency at the receiver does not coincide or does not identical to the transmitter carrier frequency. So it means that if you are moving the car around or somewhere, so you have a Doppler effect or you have a Doppler frequency, so the carrier frequency shifted to other frequency. So this trouble introduced unorthogonality of the system. So in the today morning session, I explained that if you have a Doppler frequency, so your system will suffer from the intercarrier system, intercarrier interference. ECI. So that is the effect. Yeah, suffer from in the frequency domain. So you evaluate the system performance. You need to calculate the RCI power, independent on the frequency, Doppler frequency. Yeah. And here, in the time domain, you know that the channel is suffer from the inter-symbol interference. Yeah. In the time domain, the system suffer from inter-symbol interference. Inter-symbol ISI. Okay, it's inter-symbol interference. And in this directly the inter-symbol interference directly related to the channel input response. Channel input response. So that is channel input response. Okay, or channel input response. And you know that so in order to estimate the channel, so we need to insert the pilot symbol. We need to insert the pilot symbol. So actually, in this channel estimation for the op-amp system, you can insert the pilot symbol in the time domain as well as in the frequency domain. In here, I draw here. That is the pilot symbol. Yeah, the pilot symbol. That's the pilot symbol. So what is the pilot symbol? The pilot symbol is a null symbol at the receiver. It's a null symbol at the receiver. So if you want to estimate something, you need to transmit something that you know at the receiver. So if you know the pilot symbol, then you are not able to estimate the channel. So that is the concept. So now you need to know how to insert the pilot symbol in the time domain and also in the frequency domain. In this, we have a theory and there are a lot of papers on this topic. So if you are working on the channel estimation, you need to read a lot of papers. I just show you that if you have a much larger Doppler frequency, it means that the channel is time variant or fast time variant in the time domain, that you need to insert more pilot symbol in the time. So similar in the frequency domain. So you need to calculate how you can insert the pilot in some way that the pilot not too much, not too many pilot. If you insert many pilot, then not less for data. So you have to insert the pilot, not too. So if you insert only few pilot, also not too. Because if you insert only few pilot, then you lost the channel information. And based on the pilot symbol here, is the pilot symbol here. You can also calculate the channel at the pilot position. Yeah, you can calculate. Yeah, you can calculate the channel coefficient at the pilot position. Yeah, and then based on this information, the channel information that you know at the position of the pilot symbol. You can also interpolate, or you can also predict or estimate the channel at the position of the data. So even though the channel position of the data position, you can decouple the signal. Yeah. And how you can estimate the channel information at the position using the filter. Filter help us to educate a lot of filter. Filter help us to eliminate noise. Yeah. Filter help us to estimate the channel. Yeah. Filter help us to detect the data. Even filter to help us to predict the channel condition. Filter help us to predict the data. So the filter application very wide, especially in analytic filter. Yeah. Okay. Okay. So I skip this one. I think it's very also heavy with mathematics. That I see you a convention. The convention that I have implemented here based on the theory of the analytic filter introduced by the I think also Hiking Simon is author of this book. So Hiking Simon. Yes. Okay. Thank you, sir. Yeah. So he has introduced his book. You can read it. You can check from Google. Google, just check Google. So if I write something on the book, I write something on the I write something on the line of the right table. So you can also write it and using the Google search. Yeah. Google search to check what I'm discussing, check what how to correct or wrong. Or even you can also use your mallet. You might have a mallet code. You can check if the code is not correct or not. So if you have something you not understand or not understood, you can send it. So I hope that my lecture here is not only to help you to have maybe one point, one PD, but also to help you to understand what is the wallet calculation, have a good mallet code and so good like around writing the basic or something, do something else. Yeah. I think filter theory is very difficult. Everything is for filter. And here I show you that the cost function. That's the cost function. So that's the cost function, that's the expectation of the square value square amplitude square value of the difference between the ideal one and the estimated one. Between the ideal channel and the estimated channel. Between the receiver symbol and the transmitter symbol. That's the cost function. And yeah, actually I have the cost this. I have also the code of this theory. And you, if you want, I can give to you. Yeah, I can give to you. Okay.